All right, so this video is on section 8.3, the start of it, but I did want to just go back and kind of finish this. I kind of got cut off in the last video, but if you just plug in the formula and you add the finite population correction factor and hit enter with a solve, it gives you this interval, which is kind of neat because these calculators are so good with solving these inequalities. You know, the maximum size that you could sample is 415, which is of course the population size, but the minimum would be the 558, 55, or 255. So 255 to a census. So the minimum would be 255 people. So out of the 415, you don't need to survey 660 of them. You could get it with just 255. That's what that correction factor does for you, which is kind of interesting. All right, on to the main show here. So confidence intervals for means. Suppose we want to construct a confidence interval for mu, the true population mean, when we know the true population standard deviation. How often do you suppose we would want to estimate the true population mean when we know the true population standard deviation? If you kind of said never, you're right. We'll never have this value. So it's a little bit ridiculous to talk about it, but let's talk about it. Recall when the conditions are met, the sampling distribution of x bar is centered at mu and has a standard deviation of sigma over square root of n when the conditions are met. So your confidence interval is always going to be your stat plus or minus your margin of error, which is calculated by taking the crit value times the standard deviation of the stat. So the formula is different because we use x bar to estimate mu. We're still going to use a z-crit, but now we're going to use the standard deviation of the sampling distribution of x bars instead of the square root of pq over n. And honestly, if it wasn't for this problem right here, we'd be done. That would be all there is to write, all there is to know, and we'd start calculating confidence intervals. But we're going to run into a problem. We want to estimate the weights of high school offensive linemen in the state of Texas. You take a sample of 50 kids and find their average weight to be 220. Suppose it is known that the population standard deviation is 26. That's the fantasy, right? That's the thing that you'll never really know, but assume the conditions are met and construct but do not interpret a 95% confidence interval. If a problem on the AP ever says assume the conditions are met, that just basically means you don't have to check it. Don't interpret. Basically, this question is just asking us to actually do the mechanics. So estimate plus or minus crit value times the standard deviation of your estimate. Plug in the values. 220 plus or minus 95% confidence, 1.96 times 26 over the square root of 50. So if I put that in the calculator, I think I got that right. Hit enter, it gives me the upper bound. Grab it, put a minus in between there. Gives me the lower bound. So 212.8 to 227.2. 212.8 pounds to 227.2 pounds. So that would be my confidence interval. And like I said, we'd be done. However, of course we don't know the population standard deviation, and instead we use the sample standard deviation in its place. So this is a true standard deviation. This would be the estimate for the standard deviation, also known as the standard error of x bar, which is, and this should make sense. This isn't breaking any crazy, new ground here. Instead of using the sigma we don't know, the population standard deviation we don't know, we should plug in our sample standard deviation in its place. So that's it. This is a standard error. Just put in the sample standard deviation instead. However, there is a major issue with the standard error formula. For small sample sizes especially, the standard error is not a good enough estimate for the population standard deviation. Explore this applet to figure out what's going on here. So we spent a lot of time on this in class. I'm going to try to hit all the points without making it too long in this video. So this is a applet from the Rossmann Chance site, which I think is fantastic. So let's go to means. So this is what kind of distribution we're sampling from. So we'll just say we're sampling from a distribution that's normal. We'll say the weights of football players were normal. The mean is, well, we don't know what the mean was. We never did know what the mean was. I'm just going to say it was, let's say it's 227. Standard deviation is 26. Sample size was 50. So and we're doing a 95% confidence interval. So right now it's set to a Z interval with sigma being known. So we know sigma. Let's use our normal curve and do a normal Z interval. That's what we just calculated. So here's our sample of 50 kids. Our sample mean is 234, right there, about 234. And then there's our point estimate. And then that's our confidence interval. And did we really survey 50 kids? Yeah, we did. Okay. And that's it. So let's do another one. And another one. And another one. And another one. Okay. Oh, we missed one. All right, let's actually do 100 at a time. So I did this 100 and I missed 3. That's about 97%. That's good. There I missed 7. But on average, it looks like we're capturing about 95% of the time. This one you can actually run like 10,000 at a time. It's going to take a bit of time. Just did 10,000 samples of size 50. That's pretty impressive. Looks like our capture rate's 95% as advertised. Everything is working fine. Okay? Okay, so everything should be good. I want to get one that's got vote 5. Ah, 4 is good enough. So I don't know if you can see it because it's kind of small, but every single, maybe I want to kick the sample size down to 20 because I don't want them to be so, actually I'm going to kick it down to like 10. There we go. This will illustrate what I want better. There we go. This is what I want it to look like. So let's reset this. So I want to get one that has about 5 misses, kind of what you'd expect. 4 is good enough. Okay, I want you to notice that every single one of these intervals is exactly the same width, the same length. Why might that be? Well, they're the same length because the margin of error is calculated using z-crit times the standard deviation over the square root of n. Your sample size is the same, your sigma is the same, and your z-crit is the same because it's a 95% confidence interval, right? 1.96. So of course, all of these are the same, so your widths are the same for every single one of those intervals. All right, so now let's see what happens when we don't know sigma. If we don't know sigma, then we can't plug that sigma in there. What we do instead is we plug in the s. So let's say we keep the z's the same. We're still going to use z's, but now we're going to put in s's. So let's see what happens. And these are going to be all the same. It's not going to change the samples on us. So this is the same sample. And if I go to z with s, I have 4 misses. If I go to z with s, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 misses, more than I had before. And if you look at the widths of these intervals, they're all different. Why are they different? Because I'm putting in the sample standard deviation. Now, if you take a sample of size 10, your sample standard deviation might not be 26. If you get 10 points really close, it might be 10. Or if you get them really far apart, it might be 40. There's a lot of variability in that sample standard deviation. In other words, when your sample size is small, these are not good estimators for that. If I click this small interval, see I had a really small, like a tight sample, really small interval, and then one of these really large intervals, got a really spread out sample. But what I really want to illustrate is if you run this 10,000 times, do 100,000 times, I'm supposed to be capturing 95%, but my capture rate is only 92%. So it's not working as advertised. And if you go even smaller samples, samples of size 5, it's even worse. Here you're only capturing 87% of the intervals. So I'll tell you, I was wanting to tell you my Gossett student tea Guinness beer story, but there's a guy that actually created this two distribution, but I'm not going to get into that. So the short story. What he realized when he was working with these intervals, this guy that worked at a beer company, Guinness, that he realized that his capture rate wasn't high enough. So he's kind of thinking, what do I need to do in order to capture it? Oh my gosh, how many misses are there on that? That's a lot of misses. So he said, what I need to do is I just need to make these intervals a little bit wider. So he did some pretty complex math, but he said, I got 10 misses here, 12 misses. If I just make them wider until I have the right percentage of misses. So he introduced a new model, contrary to the Z, called the t-distribution. And what's interesting about this t-distribution is it changes for different sample sizes. If your sample size is small, it's got to be more wide. Whereas if your sample size is bigger, there's got to be less error correction, if you want to call it that. But if I change this to t, you're going to see that it's going to make those intervals a little wider, so the capture rate goes up to 95%. Look at there. Now, the payout, the disappointing thing is you have to have wider intervals, but it makes them wider so you capture the right rate. So now let's go back to 10,000. So now let's run this. Is still sample size 5. I got really wide intervals, but if I repeat my sampling, notice I am capturing at 95%. So this t-distribution is a special factor that accounts for the extra amount of error introduced into your confidence interval because we're using our sample standard deviation in lieu of our population standard deviation. All right, so that's kind of the theory behind it. Let's get into the nuts and bolts. All right, I need to modify the notes. In class this confuses kids, but real quickly, don't worry too much about this. But if you remember the z-score formula, it's your score minus the mean of your x's divided by the standard deviation of your x's. So if we put this into a z-score formula, only we're using our sample means. Remember the mean of the sample means is the mean, and the standard deviation of our sample means is sigma over square root of n. So if you take your x bars, or n x bar, and you subtract the mean, and you divide by the standard deviation of the sample means, this does have a normal distribution. If sigma is known, then this value is normally distributed. However, if you substitute the standard deviation in there, he found that these are not normally distributed. And he looked at what their distribution looks like. And he came up with this alternate model called a t-distribution. Okay? And these t-distributions, there's an infinite number of them. There's a different one for every possible number of degrees of freedom, where degrees of freedom is your sample size minus 1, kind of the denominator of that standard deviation formula. So if our sample size is 20, that would be 19 degrees of freedom. There's one curve for that. Want 18 degrees of freedom? There's a different curve for that one. So these are going to be a little bit more complex to work with. Let's cover it in the next video.